In this module, we'll broaden our exposure to what the Linux operating system has to offer. We'll do a rundown of the most common Linux commands, and we'll see how we can connect the input and output streams to files or even to other programs. We'll also dip our toes into scripting in a different programming language called Bash. You might be wondering, why are we learning a new programming language when I'm just getting comfortable with Python? Well, don't bash your head against the wall just yet. Being able to script in Bash can be a really useful complement to our Python scripts. Don't worry, it's going to be a bash. Okay, I'll stop with the bash puns for now. Anyway, imagine that you wanted to convert all image files in one directory from PNG to JPEG format. There's a command called convert that you can use to do this. You could definitely do this in Python by going through all the files in the directory using os listdir and calling convert using subprocess run. But it would end up being a really complex script for something that's actually super simple. You'll soon see how you can do this in Bash with just 3 lines of code, making it more readable and a lot easier to maintain. For my job, I have to write scripts in Bash all the time. I generally opt for Bash when I need to automate just a few lines of code, and using Python wouldn't add any additional value. For example, I had to write a short Bash script recently that mounted several disks one by one and compressed and archived the data on them. Over the next several videos, we'll look at the syntax needed to do some basic operations in Bash, like conditionals or loops. You'll see how it's comparable to Python's syntax, but not exactly the same. Still, it's similar enough that it will be much easier to understand now that you already know how to program in Python. By the end of this module, you should feel much more comfortable interacting with many system commands available on Linux and creating your own scripts in Bash and knowing when to choose Python or Bash for your scripts. Remember, if your palms are sweating and you're feeling nervous about the upcoming topics, we're here with you every step of the way. Whenever you get stuck, just go back and rewatch the videos, practice on your own, and engage with your fellow learners. The best way to learn is to stick with it. We've already used a bunch of Linux commands by now, so hopefully these commands aren't too foreign. You might remember that echo is a command used to print messages to the screen, cat is a command for showing contents of files, ls is a command to list contents of a directory, chmod is a command to change permissions of a file, and so on. As we called out before, a lot of these commands come from Unix. Back in the 70s, when designing how these programs should behave, the philosophy was that they should do one thing and do it very well, which means we have a lot of commands, each for doing a specific thing. We'll go through them quickly, but as usual, we'll provide a cheat sheet afterwards that you can use as a reference. You have plenty of time to review these commands and practice on your own. So, let's get started. To create a new directory, we use the make dir command. To change into that directory, we use the cd command. As you might notice, these commands don't print anything to the screen. This is normal and to be expected. A lot of the commands that we use don't print anything when they succeed. They only print something if they fail. To check that the cd command succeeded, we can use a command like pwd to print the current working directory. Okay, we have a directory, which is empty. We can copy files using the cp command. For example, we can copy the spider.txt file that we have in the parent directory. What are all those dots? These are shortcuts that we can use to refer to some special directories. The ..dot shortcut refers to the parent directory, the previous directory in the absolute path, while the dot shortcut refers to the current directory. So, this command is copying the spider.txt file located in the previous directory to this directory. Does that connect the dots? We can also create an empty file using the touch command. So, by now we have 2 files in our directory, the spider.txt file that we copied and the myfile.txt that we created using the touch command. Let's look at the contents of our directory using the ls-l command. Nice. We've now called the ls command using the -l command line argument. Remember, Command line arguments let us change the behavior of commands, making them do what we want. Without any arguments, ls would just list the names of the files contained in the directory. By passing the -l, we get a lot of extra information distributed in a bunch of columns. Pop quiz time. What are these columns? The first column indicates the permissions of the file. The second column is the number of inodes that point to the file. The third and fourth columns indicate the owner and the group to which the file belongs. Then comes the size of the file, the date of last modification, and finally, the name. In our case, we have the file that we copied, which has 192 bytes, and another file that we created using the touch command, which has 0 bytes. Let's check out another ls command line argument by calling ls-la. The -a flag shows hidden files, which are the ones that start with a dot. In this case, the only ones are the shortcuts that we called out earlier. The dot shortcut for the current directory and the ..dot shortcut for the parent directory. The sizes of these directories are related to the amount of files in them. To rename or move a file, we use the mv command. To copy a file, we use the cp command, like we mentioned earlier. We've now renamed myfile.txt to emptyfile.txt and created a new copy of the spider.txt file. Each of these commands use the same format. The first parameter is the old file and the second parameter is the new file. Let's look at the contents of our directory now. We see that we now have 2 copies of our file with 192 bytes, and the empty file is now called emptyfile.txt. To delete these files, we can use the rm command. We can either go one by one, or we can delete them all together using the star. The star is a placeholder that gets swapped out by the names of all the files in our directory. So, our directory is once again empty. Now let's get rid of it. First, we need to change to the previous directory. We do that using cd ... Again, ... is the way we use to identify whatever was the previous directory. Alright, now we can delete the directory using rmdir. This command only works on empty directories, so it wouldn't work if we had left any files in it. This time, when calling the ls command, we passed the name of the directory that we wanted to list and got back an error because the directory didn't exist anymore. Did it ever really exist at all? It really makes you think. Anyway, that was a quick overview of some of the commands we have in Linux to operate with files and directories. There are tons of other commands to talk about, but not enough time to talk about them all. We'll mention some of them in the next few videos and put more info about them in the cheat sheet. Make sure to investigate and practice using them all on your own. Remember that reading the documentation for any given system command can help you learn more about what it does. On Unix-based systems, this documentation can usually be found in manual or man pages using the man command. Let's keep moving. Up next, we'll talk about a different aspect of the command line interaction: how to redirect I/O streams. So, now that we've covered a few basic Linux commands, let's talk more about what we can do with I/O streams in Bash. In an earlier video, we talked about the standard I/O streams. By default, the input is provided by the keyboard at the text terminal, and the output and error are shown on the screen. This is the case not only for our Python scripts, but for all system commands. We can change this default using the process called redirection. Redirection is a process of sending a stream to a different destination. This process is provided to us by the operating system and can be really useful when we want to store the output of a command in a file instead of just looking at it on a screen. To redirect the standard output of a program to a file, we use the greater than symbol. For example, take the following Python program, which just prints a single line of text using the print function. If we run this program without redirection, the text will be sent to the display using the stdout normally. But now, if we use the greater than character to redirect the output instead, something else happens entirely. When we run it this way, the stdout from stdoutexample.py script is redirected to a file called newfile.txt. If that file doesn't exist, it's created. Let's look at the contents of newfile.txt using the cat command. You see that? The output of our program ended up in the file that we wrote after the greater than symbol. Beware, just like we saw earlier with the W file mode used by the open function, each time we perform a redirection of stdout, the destination is overwritten. So, we need to be super careful when using this redirection that we're not overwriting a file with valuable contents. If we want to append the redirected standard out to a file, we can use the double greater than sign instead of a single greater than. Isn't that great? In a similar way, we can also redirect the standard input. Instead of using the keyboard to send data into a program, we can use the less than symbol to read the contents of a file. Let's try this out with a new version of the streams.py file that we saw in an earlier video. Okay, now let's redirect the contents of our new file to this script. Awesome. In this case, we don't see the input on the screen in the stdin portion. This is expected because the input was read from a file. So it only appears in the stdout portion where we see that it read one of the two lines. This is also expected because the input function only reads until it encounters a new line character. It can also be useful to redirect stderr to capture errors and diagnostic messages from a program. This can be done by using the character combination =, similar to how we redirected stdout before. Let's execute our stream example again, this time redirecting the error output to a separate file. So this time, we don't see the error message on the screen. That's because we redirected it to the error file. Let's see if we can find any goodies in the contents of that file. Aha! There's our error. If you're wondering about the number 2, it represents the file descriptor of the stderr stream. In this context, you can think of a file descriptor as a kind of variable pointing to an I/O resource. In this case, the stderr stream. 0 and 1 are the file descriptors for stdin and stdout. Like we called out already, none of this is exclusive to Python. We can operate in the same way with all other commands. For example, we can create a file using the echo command and redirecting its output to the file that we want to create. Boom. And as usual, we can see the contents of our new file using our friend cat. Alright, so now we've seen how we can redirect input and output to files. How about redirecting between programs? On top of the redirection to and from files that we saw in the last video, there's another powerful way to perform I/O stream redirection called piping. Using pipes, you can connect multiple scripts, commands, or other programs together into a data processing pipeline. Pipes connect the output of one program to the input of another. This means we can pass data between programs, taking the output of one and making it the input of the next. Pipes are represented by the pipe character. Using pipes is an extremely useful tool. It allows us to create new commands by combining the functionality of one command with the functionality of another without having to store the contents in an intermediate file. So let's work on our plumbing, shall we? Here's an example. Here, the output of the ls-l command is connected to the input of the less command, which is a terminal paging program. This example can be pretty useful when you want to look at the contents of a directory containing lots of files. The list of files generated by ls is piped to less, which displays them one page at a time. We can scroll up or down using the page up, page down, or arrow keys. And once we're done looking at the files, we can quit with Q. But it doesn't have to stop there. It's possible to connect a lot more than just two programs using pipes. We'll check this out using a more elaborate example. That's a complex command line. Let's go through it step by step. We're first using cat to get the contents of our spider.txt file. Those contents are then sent to a command called tr, which gets its name from the word translate. It takes the characters in the first parameter, in this case it's a space, and then transforms them into a character in the second parameter. In this case, it's a new line character. So basically what we're doing is putting each word in its own separate line. Hooray for organization. Next, we pass the result to the sort command through a pipe. This command sorts results alphabetically. The sorted results are then passed to the unique command, which displays each match once, and by using the -c flag, it prefixes each unique line with the number of times it occurred. This output is passed via pipe to the sort command once more, this time with the -nr flag, which sorts results numerically and in reverse order, from most to least hits. The output is finally passed to the head command, which prints the first 10 lines to stdout. Whoa, that's a lot to process. But when you break it down, it makes a lot of sense, right? The point isn't to memorize all these commands, but to know that we can pipe as many commands as we need to do exactly what we want. You can use your Python scripts in pipelines too. Python can read from standard input using the stdin file object provided by the sys module. This is a file object like the one we obtained using the open function. And, like your local library, this file object is already open for reading. Let's say we want to write a script that reads each line of the input and then prints the line with the first character in uppercase. To do this, we'll take advantage of the capitalized string method. It'll look something like this. In this script, we're iterating over the contents of the sys.stdin file. Remember that when we iterate a file object, we go through it line by line. For each of the lines of a file, we first use the strip method to remove the new line character at the end, then capitalize method to make the first character of the line uppercase, and then we print it out to standard output. Now, let's use a script to capitalize a file that we have in our computer called haiku.txt. Let's see the contents of it using cat. Shakespeare couldn't have said it better. Now, let's use a pipeline to capitalize our haiku by combining the output of the cat command with our capitalized script. The cat command sends the contents of the haiku.txt file to standard output, which we redirect to our script using a pipe. Our capitalized script uses the sys.stdin file object to iterate through each line of standard input, printing the capitalized version to standard output. It's truly poetic, isn't it? We should also call out that we don't need to use a pipe to get the contents of the haiku.txt file into standard input of our script. Instead, we use the redirection operator we saw in the last video, like this. As a rule, if you just need to get something from standard input into your script, using a redirection is enough. But if you want this to be part of a bigger pipeline of commands, you'll need to combine them with pipes. For example, if we only want to capitalize the lines that match a certain pattern, we could first call grep and then connect it with a pipe to our script. With a little practice, creating pipelines is a fast and powerful way to perform lots of system administration tasks. When a system command doesn't exist with the functionality that you need, you can write a Python script to fill in the gap and include it in your pipeline. Understanding how to redirect I/O streams can come in handy in many situations and when writing code too. We'll see plenty of more examples of this down the pipe. Get it? Pipe? Okay, sorry. Up next, we'll dive into the different ways we can send signals to the running processes on our computer. When dealing with the operating system, we usually have a bunch of different processes that we use to accomplish what we want. And like any well-oiled machine, we generally need these processes to communicate with each other. For example, we might have a program that starts a background process and wants it to terminate after a timeout. One way of communicating this is through the pipelines we learned about in the last video. Another way of communicating is through the use of signals. Signals are tokens delivered to running processes to indicate a desired action. Using signals, we can tell a program that we want it to pause or terminate. We can also cause it to reload its configuration or to close all open files. Knowing how to send these signals lets us interact with processes and have more control over how they behave. There are a bunch of different ways that we can send these signals. For example, let's execute the ping command in our terminal. The ping command is now running, sending ICMP packets to a machine over the network once per second. And it will keep running forever unless we interrupt it. To do that, we can use the Control-C combination. See how when we interrupt it, the program doesn't just end abruptly. First, it prints a summary of what it did and what the results were. It's very polite under these circumstances. What's happening behind the scenes is the process received a signal indicating that we wanted it to stop. When that signal is received, the process does whatever it needs to finish cleanly. The signal that Control-C sends is called SIGINT. It's just one of many signals that we can send. Another keyboard combination that we can use to send a signal is Control-Z. Let's try this one out. So, our ping is running once more. This time, we'll interrupt it with Control-Z. Uh-oh, this time the process didn't finish properly. We get a message saying that it stopped. What's going on? The signal that we sent is called SIG-stop. This signal causes the program to stop running without actually terminating. But don't worry, we can make it run again by executing FG. The FG command makes our program run once more. And it'll keep going until we interrupt it, either with Control-C, Control-Z, or some other signal. Let's stop it now with Control-C. By pressing Control-C this time, we've made the program finish cleanly. To send other signals, we can use a command called kill. Yikes. By default, kill will send a signal called SIGTERM that tells the program to terminate. Since kill is a separate program, we need to run it on a separate terminal. And we also need to know the process identifier, or PID, of the process that we want to send a signal to. To find out the PID that we want to send a signal to, we'll use the PS command, which lists the currently running processes. Depending on what options that we pass, it'll show different subsets of processes with different amounts of detail. For this example, we'll call PSAX, which lists all of the running processes in the current computer. And then we'll use the grep command to only keep lines that contain the name of the process that we're looking for. Sound good? Okay, let's try this out. We'll run ping on one terminal and then find its PID and kill it from a second terminal. Cool. So our PS and grep commands found that the PID for the running ping command is 4619. We can now use this identifier to send the signal that we want using the kill command. We've now sent the SIGTERM signal and the process was terminated. Hasta la vista, process. Notice how in this case, we didn't get the nice summary at the end. The program just finished. As you might expect, there is more signals that we can send, and they might cause programs to react differently. Many long-running programs, for example, will reload their configuration from disk if we send them a signal. This way, we can let the program know that there's an important change in the configuration and it can get applied without the program having to stop to reread it. Programs that provide web services might also receive a signal to tell them that they should finish dealing with any currently open connections and then terminate cleanly once it's done. Understanding what these signals are and how to send them will let you interact with the processes on your system that you're in charge of and make them behave as you want.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.